Hello, welcome to Can We Do That Some More, the accompaniment videos to the main Can We Do That series, which provide us with the opportunity to either add extra details to do with the concepts covered in those mainline Can We Do That videos, as well as providing you with practice questions to try yourself, along with the work solutions for said questions. In today's video, we're focusing on the topic of integration by first principles using Riemann and Darboux sums. Apologies in advance, as you can probably see this video is rather long, and that's because it's going to be split into two main sections. In the first section, we're going to be having a focus on the notation associated with this area of mathematics, so that you can understand what it's actually telling you, and so therefore you're not put off by it, because I know that a lot of really complicated math notation looks a bit imposing. And then in the second part of the video, we're going to be doing the usual thing we do in the Can We Do That Some More videos by providing you with some questions on this topic to try yourself, and then me going through those questions so that you have the work solutions for them as well. And as usual, the warning that although this channel has a focus on preparing students for the A-level qualifications in England, in reality every video in this particular Can We Do That Some More series is not covering content that you do need to know for those exams. So therefore don't worry about it, this stuff is for fun. And with that warning out the way, let's start by taking a look at the notation associated with a Riemann sum. If you have the Riemann sum for a function f over a tagged partition, that will look something like this, given a tagged partition defined in this way. However, there's already a lot to unpack there straight away. What even is a tagged partition? Some of you might be asking. Well, let's explain that by first looking at what a partition is. If you start with an interval, you can split it up by fitting more numbers in between the start and the end point of that interval. Those numbers that you're fitting in between there will then form the start and end points of a bunch of subintervals that you're splitting that original interval up into. These intervals are then acting as the partition. But then to convert the partition into a tagged partition, you basically need to select each of these subintervals and just choose one particular x value from each of those subintervals. If you do that for all the subintervals, you have a tagged partition. And so therefore you can already see that that's effectively what we are defining with that bottom part of this notation, defining the partition first and then making a tagged partition by selecting one x value from each of those subintervals. That then feeds into how we both define and calculate a Riemann sum, because when we're integrating something, we integrate it over an interval. And then that interval, the first number in that interval ends up being the first number in the partition we're splitting up into, and the last number in the interval becomes the last number in our partition. Then, of course, when we're calculating a Riemann sum, we're effectively trying to estimate the area using a bunch of rectangles. And that partition will effectively provide us with the start and end points for each of those rectangles. The height of the rectangles can then be calculated by selecting the x values we chose as part of forming the tagged partition and plugging them into the function we're trying to integrate. Those x values are chosen specifically to be the points at which the tops of the rectangles are intersecting with our function. Those function values can then be multiplied by the width of each rectangle, which can be calculated by working out the gap between each consecutive pair of values in that partition. And therefore that's why the Riemann sum has this sigma notation format that you can see right there. Sigma meaning sum of each of the areas of those rectangles calculated in the way we just specified. So that's Riemann sums, but what about Riemann integrals? How do we know if something is Riemann integrable or not? Well, in the main Can We Do That video, we provided this definition here. However, there's a lot of complicated stuff going on here as well, so let's unpack that too, starting off by looking at what this term mesh means. A mesh is ultimately just the length of the longest subinterval in a partition. By taking another look at the example we had before, by applying this partition to the interval 2, 9, this led to these subintervals, and then we can work out the lengths of each of those subintervals by working out the gap between the bounds, which would lead to these numbers here. You can clearly see that the biggest length is the number 3, therefore meaning the mesh for this partition would be 3. It's that easy, so therefore we can now take a look back at this definition and try to unpack what it means a bit more. Of course, this bit here was just the definition of a Riemann sum that we were just looking at, and as this definition is already stated at the top, I is the actual answer to the Riemann integral. So therefore, if you're doing this calculation, you're effectively calculating the error in your calculation, the difference between the actual proper answer that it's meant to be and the current answer you have with the Riemann sum that you've currently got. We're trying to make sure that this error is below a certain value. And therefore, this is starting to reflect the process that we were doing when we're calculating the limit as n tends towards infinity. N was of course a measure of how many rectangles we're using, but the more rectangles we're using, that would mean the width of each rectangle must be getting smaller if we're fitting them all into the interval. Therefore, that's talking about the mesh getting smaller. And therefore, what this definition we can see on the screen right now is trying to tell us is that if you want to make the error in the calculation of our Riemann sum smaller and smaller and smaller, you'll need to make the mesh smaller and smaller and smaller, which means you need to make the value of n get bigger and bigger and bigger forever, hence why n was tending towards infinity. This definition has an interesting knock-on impact though, because it helps define why improper integration doesn't fit under this umbrella of Riemann integration, which is that, of course, if you're trying to calculate an integral with an infinite value, then that's a problem, because this error calculation here will be infinite, because if you try and do arithmetic with infinity, it basically doesn't work, and therefore that's stopping us from being able to put that selected bound on the value of this error. We can't just keep on making that error smaller because it will automatically be infinity the moment I is infinite in any sort of way. And what about Darboux integrals? Let's take a look at Darboux sums first of all, and again you need to start by defining what function you're dealing with as well as a tagged partition, because ultimately Darboux sums are still calculated using the areas of rectangles. But then once you've defined things in this way, you can define the lower Darboux sum by this calculation here. We often use this notation with that L to define the lower Darboux sum because the L stands for lower Darboux sum, and then the function and the partition you're using can then be inserted into that notation as well if necessary. You'll notice that instead of calculating the height of the rectangles by just using the x value from the tagged partition and plugging it into the function, we are now also taking the inf of that value, which is short for the infimum. Similarly, the upper Darboux sum is calculated in a very similar way, but instead of the inf, we're taking the sup, which is short for supremum of that thing inside those brackets. But what does the words infimum and supremum actually mean? Well, they're related to minimums and maximums respectively, but they are slightly different. So let's take a look at that distinction now. If you're trying to calculate the infimum of the interval x is between 5 and 9 inclusive, then actually that's the same question as effectively asking what's the minimum of that interval. The answer is just going to be 5, and that's because there is a defined minimum value in that interval. However, if you're trying to find the minimum value of this interval, it's actually not going to be possible because there is no single defined minimum value, because you can always find another value smaller than the value you previously found that's still in that interval. For instance, if you had 2.1, you could have 2.01. If you had 2.01, you could have 2.001, so on and so forth forever. So that interval doesn't have a minimum, but it does have an infimum, which is just going to be 2. So the difference between infimum and minimum is that the infimum is just not necessarily always actually in the interval that you're finding the minimum inverted commas of. And in return, it's the same relationship between the word maximum and supremum. So that's all that's going on there. Therefore, taking a look back at this definition, this is then relating to what I was saying in the previous video about the fact that you want all the rectangles in the lower Darboux sum to be providing an underestimate. So therefore, the top of the rectangle has got to be using the smallest y value in the interval for which the rectangle is valid. And then for the upper Darboux sum, you want the rectangles to be providing an overestimate. So therefore, the height of the rectangle has got to be using the maximum y value in the interval for which that rectangle is valid. The lower Darboux sum and the upper Darboux sum are then providing the bounds for the overall Darboux integral. But if you have bounds on something, in an ideal world you want those to narrow in so that you end up with just one single value for what you're trying to find. You want, in other words, the smallest upper bound and the largest lower bound. Therefore, to find the lower Darboux integral, you just have to find the supremum of the lower Darboux sum. In other words, as I just said, the highest lower bound possible. And to find the upper Darboux integral, we're going to find the infimum of the upper Darboux sum. In other words, the lowest upper bound we can find. Now, that sounds all very complicated for Darboux integrals, but the good news is that if you're just dealing with a nice continuous function, then calculating the lower Darboux sum and upper Darboux sum can just be done using Riemann sums effectively. As we explained, whether you're doing a left or a right Riemann sum to find the lower Darboux sum is all dependent on whether you've got a decreasing function or an increasing function in the interval you're integrating. And then also conveniently, although this then supremum and infimum of the upper and lower Darboux sum stuff then seems to be adding a further level of complication, the convenient thing is if you make n tends towards infinity for simple integrals such as polynomials and stuff like that, then that will have the same effect as finding the highest lower bound and the lowest upper bound, just because of the way the functions work and where the value of n ends up in those calculations. Cool, and that does bring to an end the first section of this video, covering the various notation associated with this stuff, and I hope you found it useful for helping to start to explain what this notation is trying to tell you. On to the second part of the video, where I'm going to provide you with these questions. At this stage of the video, welcome to pause the video, have a go at them yourself, and then if you're interested, stick around because I will be going through the solutions to all these questions so you can check whether you were right or not. Right, let's have a go at these questions, and I must admit, I absolutely love this stuff. I know there's sometimes maybe a tendency with mathematicians to sometimes look down upon topics they've learnt a time ago to instead replace them by the new shiny complicated thing they've been learning more recently. But I think there's always merit in being able to look back at maths you've learnt before and appreciate it for what it is, to be able to see the beauty in it, if you will. And that's very much the case for this particular topic, along with differentiation by first principles. I just love how it just neatly shows results that we're able to do in a more quick way normally, but just kind of showing the reasoning behind them, if you will. So in this one, we're doing a right Riemann sum to calculate the Riemann integral for this particular integral as given. A little bit of advice I'd give is drawing diagrams for this stuff, not because you have to. I mean, none of this stuff is being marked. We're doing this stuff for fun, certainly from the context of this video anyway. But it doesn't hurt to draw a diagram just because it helps get your head around exactly which x values you need to be using to work out the heights of the rectangles that you're working out the area for. So it always helps with that sort of stuff. So in this case, we're doing a right Riemann sum, so that means I need to make sure, if I can speak properly, that I'm drawing the rectangles so the top right hand corner of them is touching the function. So there we go. The rectangles were meant to be equal in width. They haven't been drawn that way. That's just terrible drawing. Apologies. But we're going from 0 to 7. Now, therefore, that means if we're having n rectangles in between 0 and 7, the width of each rectangle is going to be 7 take away 0, all divided by n, which would be 7 over n, unsurprisingly. So there we go. But what does that mean? Well, it means the end of the first rectangle is 7 over n. The end of the second rectangle would be 2 lots of 7 over n, etc., etc. And therefore, the x values we're going to be using to plug into the equation to get the y values form a sequence which would have the nth term of, except it wouldn't be nth term because r is the variable for this sequence, but it would be 7 over n lots of r, like so. That's quite nice because then it means we can work out the sequence giving the y coordinates for these points that are here, 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 etc., etc. And that would basically just be formed by taking our x values and plugging into the function. So 3 lots of 7 over n lots of r all squared, like so, which of course you could go ahead and simplify, but really I'm not going to fully simplify them. I'm going to keep the 3 out the front. That's because I know later on we're going to be dealing with the sum of r squared, which I know is a formula, has a 1/6 in it, which is just going to cancel out that factor of 3 out the front later anyway. So I'm not going to bother fully multiplying it out because I know I don't need to. You could, but you don't need to. So there you go. Therefore, the Riemann sum would be given by the sum from r equals 1 to n of the area of these rectangles. The area of the rectangles would be formed by multiplying the base or the width of each rectangle times by its height, and the height is given by those y coordinates that we were writing just a few moments ago. All a bit crammed, I'm very sorry. There you go. You could then simplify that. Again, I'm going to leave that factor of 3 all the way out the front, just because that's going to make my life a lot easier to do so, just because I know no point multiplying out, it's just going to cancel out later. We've got the 7 times by the 49, which should get 343, and then we've got an n cubed on the bottom, and then we have r squared. Nice! So that would be the Riemann sum, but we actually need to calculate what that would be in terms of n. And then also, the other fact is we're calculating the Riemann integral. So therefore, to convert it into the Riemann integral, we basically need to apply a limit to that thing that we had there. So it would be the limit as n tends towards infinity of that summation we were just looking at, which was from r equals 1 to n, 3 lots of 343 over n cubed, lots of r squared. Cool. So now we can go ahead and continue working this stuff out. So therefore we can now use the series formula for r squared, which would be, what would it be? It would be 3 lots of, what am I talking about? It's not 3 at all, it's 1/6 lots of n plus 1 to n plus 1. There you go, got my brain in gear eventually. Close the brackets, lovely stuff. The 3 and the 1/6 are going to cancel out to leave a half, so we're going to end up with 343 over 2n cubed. I've forgotten the lim notation, that's dreadful. Let's sneak it in right there at the front. And then we've got those brackets all being multiplied out. And that will come to, if I skip a bunch of steps without multiplying out bracket stuff, you will get 2n cubed plus 3n squared plus n. And that's quite nice actually, because then it means I'm going to keep the 343 out the front for the moment. You'll see why very soon. But I'm then going to write the polynomial we had, all divided by the 2n cubed. I'm going to simplify it a bit for the individual fractions. So we'd end up with 1 plus 3 over 2n, and then lastly n divided by 2n cubed would be 1 over 2n squared, like so. Now the reason I've chosen to write it like that is now if you make n tend towards infinity, you'll notice the only place where n is now appearing is in the denominator of all these fractions, which is great news, because if that's the only place n is appearing, as n tends towards infinity, those fractions with n in them are all going to tend towards 0. So therefore that's just going to leave us with the only term in that, not polynomial technically, in that expression, let's say, that doesn't have an n in it, to be left behind, which is that 1. So as n tends towards infinity, we're just going to be left with 1 lot of 343, which is 343. Amazing. And funny enough, if you were to calculate the integral in the more quick traditional format of 3x squared between 7 and 0, you would get 343. So there you go. Amazing stuff right there. Let's have a go at a second question though. This time we're calculating a middle Riemann sum to work out a Riemann integral. Interesting, because I didn't actually go through any middle Riemann sums in the main Can We Do That video, but in reality something I did just point out is it's just changing exactly which x value you're using to calculate the y value, but it's still a similar idea of working out some rectangles ultimately. And to help with it, once again, I'd just recommend drawing a diagram, because it makes your life a lot easier for knowing how you're going to start calculating said rectangles, etc., etc. So this is a very rough diagram. If we're doing the middle Riemann sum, what that means graphically is when I'm drawing my rectangles, I need to make sure the middle of each rectangle is what's intersecting with the function. So the middle of the top of each rectangle, if we're being more specific there. So that's why I'm drawing it like so. We're starting at 9, finishing at 14. That means the width of each rectangle, if again we've got n rectangles, it'd be 14 take away 9 divided by spread between n rectangles, which would be 5 over n. So that's the gap between each rectangle. But the interesting thing is I'm not interested in just adding that on each time, although that would get the end of the first rectangle, for instance, if I added on 5 over n. What I really want is what's the x value for halfway into that first rectangle, which would be got by doing that first rectangle's start point plus half of the width of a rectangle, which should be 5 over n divided by 2, in other words 5 over 2n. Cool. Now the interesting thing is the next rectangle, midpoint, is still going to be very easy to calculate, because although the start point is a bit more fiddly this time, still how we get from one rectangle to the next is still the same as it is for all the Riemann sums. It's still going to be a width of one entire rectangle to get from the first x value to the next x value. So therefore it's going to make use of sequences and series knowledge to write this sort of stuff. Admit that you could do even more simple stuff if you wanted to work out the sequence term if you wanted, but arithmetic sequence knowledge would help you, because you know that the nth term, inverted commas, it's not nth term, the nth term would be of course the first term, which in this case we're saying is 9 plus 5 over 2n, plus the common difference, lots of r minus 1. So therefore the common difference in this case is 5 over n, and we're doing that amount of r minus 1. I'm going to simplify that because it makes sense to do so, because some terms are going together, because we're going to have 5 over n, lots of r, minus 5 over n, and 5 over 2n minus 5 over n is just going to be minus 5 over 2n. So there we go, we've got marginally less stuff to write there. That means the y coordinates are going to be formed by just plugging those x values into the function, because that is when we'll meet these points here that form or match with the heights of the rectangles. So therefore, that's just going to be 2 lots of that sequence we just mentioned. So therefore, that multiplies to get 18 minus 5 over n and plus 10 over n lots of r, like so. Brilliant, which means we can move on to working out the Riemann sum, and the Riemann sum would just quite simply be the sum from r equals 1 to n of the area of the rectangles, which would be the base times by basically all of these things we've got there, because we already mentioned that's effectively the height of the rectangles. Nice, but we then actually need to work that out to convert it into a Riemann integral, as well as applying the limit that we're normally meant to do. So therefore, we're doing the limit, as n tends towards infinity, of the sum from r equals 1 to n of all that stuff we just mentioned. Hopefully I can remember it without referencing the stuff on the previous slide. I think I can. I think that's right. We'll find out at the end soon enough if I've got that horrifically wrong. Okay, so to deal with this, I'm first going to multiply the brackets. Admittedly, you could choose to move that 5 over n out the front of the sum, but in the long run, I'm going to have to do this multiplication anyway. So completely up to you whether you do or don't do it at this stage or not. I'm choosing to, so whatever. That will get me 90 over n. Minus 25 over n squared, and then we're going to end up with a cheeky 50 over n squared lots of r. There you go. Okay then, so now we can apply the series formula to various parts in there. The first part of the series that we're trying to calculate there is just a constant from the perspective of that sigma notation, because the variable for the sigma notation is the r value. So therefore 90 over n minus 25 over n squared is being treated like a constant. So therefore the series formula for a constant is just timesing it by n. So that's quite easy. And then the series formula for r to the power of 1 is just 1/2 n lots of n plus 1. And we've just got to do a load of algebra simplification there nicely. Some of that earlier stuff does simplify a bit. We're going to end up with a 90 minus 25 over n. And then the 50 and the half are going to combine to make a 25. And then the n and n plus 1 all divided by the n squared will get us n squared plus n all divided by n squared, which then can be simplified some more. Because the n squared over n squared will get us a, well, basically just 1. And the n over n squared will get us a 1 over n. Now, as it happens, if you were to multiply out the brackets, you could do that, because if you were to do that, you realize we've got minus 25 over n, and we've got a positive 25 over n, meaning we're technically just working this out. You could skip the step and just choose instead to work out the limit. Either way, basically you see that what we've ended up with is something where the things with n in didn't matter anyway because they're cancelling out, meaning we're just left with the limit as n tends towards infinity of 115, and the limit as n tends towards infinity of 115 is just 115 because there's no n's to tend toward infinity anymore in that expression. So there you go. That's the second one done. That was interesting that the n's cancelled out. So that's something worth noting. Would that always happen? No, it's probably just a combination of the function we were doing there, along with the fact that it was a middle Riemann sum. So something to bear in mind. Okay, moving on to the Darboux integrals, which seemed like, ooh, it's a new thing, different to what we're doing in the first two questions. But in reality, because we're still dealing with a polynomial, and because that polynomial, as you'll see in a few moments, is either just decreasing or just increasing for the entire interval we're doing the integral over, doing this is just going to involve doing Riemann sums as part of it. If you have a function that is not continuous, then Riemann sums aren't what you do anymore. If you've got a function that is got parts that are increasing and separate parts that are decreasing within that interval you're dealing with the integral for, then again just doing a single Riemann sum by itself won't be enough to do a Darboux integral. But if it's a nice simple one like this, I say simple, you might disagree when seeing the algebra, but you know, graphically simple, then actually, interestingly, Riemann sums can help us work out the Darboux sums. Again, really important we draw a diagram, and that's because for Darboux sums, even if you are aware that we can just use Riemann sums to sometimes work them out, it depends on whether your Riemann sum will be calculating an overestimate or an underestimate for the area as to whether you are going to be counting that as the lower or upper Darboux sums. So therefore, let's start by drawing our diagram. We've got a 50 minus 4x cubed. That would look something very roughly like this. Terrible drawing, but it'll do. Between 0 and 2. And therefore, if I was to draw my rectangles first of all like this, then that would be interesting because it would mean my rectangles are forming an area that's fully below the curve while still matching the curve in certain places. So that's important because it means this, as just a bunch of rectangles, would normally be what we would call a right Riemann sum. But in the context of this, as it's an underestimate, this is actually going to form what we're going to call the lower Darboux integral. As I said, don't just assume every right Riemann sum will always be a lower Darboux sum. It won't be that case. Did I say lower Darboux integral? It's related to that as well, but I meant lower Darboux sum. Because, as I said, it's only because it's an underestimate for this particular curve that this particular Riemann sum is also helping us provide a lower Darboux sum as well. Cool. Whew. Right then. Let's start working some stuff out. We are fitting n rectangles between 0 and 2, so that means, unsurprisingly, the width is 2 over n. That means for this particular set of rectangles, the sequence of x values for it would be fairly simple. It's just going to be 2 over n lots of r, because the first rectangle's height is decided by 0 plus 2 over n, so just 2 over n, so on and so forth. So therefore, we can work out the lower Darboux sum. I haven't defined what f and p are. I technically should do that. I'm not going to, because I don't want to, but that's something you should technically do. But anyway, the lower Darboux sum, given by the fact I've written the letter R, L there, sorry, would be the sum from r equals 1 to n of the base of each rectangle, which is 2 over n, times by the y-coordinate. And the y-coordinate would be 50 minus 4 lots of our x-coordinate cubed, but our x-coordinate is 2 over n lots of r. So there we go. We've now got to work out what that is. How nice. Not nice, maybe. Your opinion. The first thing we're going to get there is a 100 divided by n. And then I'm going to do a whole bunch of multiplying out here. You probably shouldn't do this much multiplying out in one big go because it's probably likely to lead to silly mistakes. I might make a silly mistake. We'll find out soon enough. We're going to be cubing the 2 over n lots of r. So 2 cubed is 8, times by 4 is 32, times by another 2 is 64. And it's a minus sign, so minus 64. We've got the n being cubed, multiplied by no other denominator, but then multiplied by an n later. So therefore that would get us an n to the power 4. And then we have luckily just the r cubed, like so. We can now apply some series formula to that. 100 over n, effectively being treated like a constant term. So therefore that would be 100 over n times by n. And then the r cubed bit will also be replaced with the formula for the series for r cubed, which is 1/4 n squared n plus 1 all squared. Obviously, the 100 over n times by n is just going to form 100. But this next bit is interesting. The 64 divided by 4 is just 16, minus 16 technically. And you could choose to, do this in more steps. I'm going to save a bit of time just because I know n plus 1 all squared by binomial expansion is n squared plus 2n plus 1. You then times it by an extra n squared and dividing by an n to the power 4. That will lead to you getting the following fraction, which is n to the power 4 plus 2n cubed plus n squared divided by n to the power 4. And you could choose to multiply the brackets. I'm not going to bother because I know what we're heading towards later with stuff we're going to do with limits. So I'm just going to simplify the fractions, or split the fractions up, I should technically say, which will lead to 1 plus 2 over n plus 1 over n squared. So that's our lower Darboux sum completed. What about the upper Darboux sum? Again, we're going to want to draw a diagram to make sure we're doing the upper Darboux sum correctly. So again, terrible drawing for the curve. It'll do. But this time, I'm going to use a left Riemann sum. So it's not a Riemann sum, because we're not doing a Riemann sum, we're doing Darboux integrals. But the point is, it's the same calculation you do for a left Riemann sum. So all the left-hand side of the rectangles are touching the curve. Basically what that's meaning is the rectangles are touching the maximum y value in the interval for which the rectangle applies. relating back to what we were talking about earlier. That's what defines an upper Darboux sum. Lower Darboux sum, as we said, is the minimum y value in the interval for which the rectangle applies. Cool. So in this case, to do that, that's why we have to do the left-hand side of the rectangle touching the curve, just because it's a decreasing function. So the biggest y value happens to the left in the interval for each of the sub-intervals created by the partition. So, therefore, once again, though, it's still going to be 2 over n is the width of each rectangle. But interestingly, the first rectangle, the x-coordinate we want is 0. The next one we want is 2 over n lots of r. Sorry, just 2 over n. Why am I doing that? 2 lots of 2 over n, etc., etc. And so, therefore, that's important because it means this time the x-coordinates are a bit more fiddly. This time it's going to be 2 over n lots of r minus 1, because then x1 will be 1 take away 1, lots of 2 over n, hence 0. The first x-coordinate that creates a y-coordinate for the rectangles is 0. So that's a bit annoying because it means the y-coordinates are going to be more fiddly to work out. They're going to be 50 take away 4 lots of 2 over n lots of r minus 1 all cubed. Lovely. But therefore, the upper Darboux sum, again, I haven't defined what f and p are. We can just assume the function the integral is being applied to and the partition to do with, what we're doing. But it would technically be the following stuff. So r equals 1 to n of the width of each rectangle, which is 2 over n, but now multiplied by this sequence of y values, which is not particularly nice, to be completely honest with you, but it is what we have to deal with nonetheless. So this is now going to take a lot of multiplying out of brackets. Apologies in advance, probably not the most interesting thing to look at in the world, but it must be done. So we're going to have 100 over n minus 8 over n. Lots of, this time I'm going to do it in multiple stages because I know otherwise it will all go horrifically wrong. So the 2 cubed gets 8, the n cubed gets n cubed, unsurprisingly. I'm on r minus 1 all cubed. I'm going to, technically I could write an extra step there, but I'm just going to jump straight to doing binomial expansion there. And all of that is included, or having the sigma notation applied to it to be more precise. We've then got the joy of dealing with all of this stuff. So the 100 over n has then got the series formula for that applied. We could now multiply the 8 and the 8 and the etc, etc. So that would get us minus 64 over n to the power of 4. And then what we can do is now apply all the series formulas for those individual bits. Whew. So that's going to be a quarter n squared n plus 1 squared minus 3 over 6 lots of n plus 1 2n plus 1, and also plus 3 over 2 lots of n plus 1, and lastly minus n. Blimey, that was a lot of stuff writing out there, a lot of stuff that needs to be multiplied out. We're going to do it. First bit is 100. Next bit, 64 divided by 4 is 16. And then you've got the individual fraction that you've got there, which we could later simplify. Maybe we'll do it, but that's the same stuff we're dealing with earlier, funny enough. So that's just going to be n to the power of 4 plus 2n cubed plus n squared, all divided by n to the power of 4. Is that going good so far? I believe it is. We'll find out later if I've made any absolutely horrific mistakes. Always a possibility. But anyway, we've got the 1/2 being multiplied by 64, which is a minus minus, so it's a plus, and it's a half, so 32. We've got the n to the power of 4 still there. And then, I don't know why I didn't absorb that inside like I did for all the others, but oh well. We've got 2n cubed plus 3n squared plus n, like so. We then have we're still going on. That's how crazy this stuff is. 3 over 2 times by 64, which is 96. It is going to be a minus, so it's minus 96. We have the n to the power of 4, so it's n squared plus n all over n to the power of 4. And lastly, we've just got the boring, well, it's going to be a plus, but it's 64 over n cubed. Cool. Now, if you were to look at all that stuff, there's a whole bunch of stuff that could simplify there. Ultimately, you can see we've got 100. We've got the minus 16. We've got, well, basically just that really for the things that are the same size. So that's an 84. We've got the other things. Actually, am I going to bother? Okay, here's the point. Here's the point. We know this is the lower, no, this is the upper Darboux sum, sorry. And the thing is, what we got to do now is we've got to take the lower Darboux sum and the upper Darboux sum, and we've got to find the infimum of the upper Darboux sum and the supremum of the lower Darboux sum, which needs to be calculated in different ways for those things normally, potentially depending on what scenario you have. But again, because we have the really nice situation of just having polynomials, the quick way of doing that for both cases is just to do the limit of n as n tends towards infinity, because conveniently that does find the infimum of the upper Darboux sum and the supremum of the lower Darboux sum. It just conveniently works out that way. So therefore, we know the integral from 2 to 0 of 50 minus 4x cubed dx is going to be greater or equal to that lower Darboux sum we had earlier, which is 100. Lim as n tends towards infinity of, as we said, 100 minus 16 lots of, what was that? 1 plus 2 over n plus 1 over n squared. I managed to squeeze it in there. Just about fit it. There you go. And then you also got to do the lim as n tends towards infinity. I can't even bother to rewrite it out. The upper Darboux sum, basically. Too big to write out again. Too many terms. We'll work it out in a couple of seconds. So, interestingly, first one, really easy to work out. The limit as n tends towards infinity. You'll notice, again, the n is only appearing in fractions in the denominator. So as n tends towards infinity, all the fractions will tend towards 0, leaving you with 1. So you end up with 100 minus 16. Shock horror. And then the lim as n tends towards infinity of the upper Darboux sum that we're looking at earlier. Interesting, you'll note that for a lot of these, the highest power of the polynomial is smaller than the highest power of the denominator. The power of the denominator was power 4, and for the r squared, r, and constant summations that we did, the highest power on the top is not as big as 4. So the only one that's actually going to matter is this n to the power 4 in the r cubed summation. So therefore, as n tends towards infinity, you're going to end up with that bit tending towards what this entire fraction here tending towards 1. So we're going to end up with, funny enough, 100 minus 16 as well over here as well. You could have multiplied it more of the brackets than I did there and fully sort of justified it by writing it as 100 minus 16 lots of something plus 32 lots of blah, 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 blah. You'll just end up with that eventually anyway. It makes it easier to justify. That sort of skipped maybe some of the justification about why the limit goes to what it goes to. But interesting, that therefore means either way we get 84, and therefore by squeeze theorem we can say the Darboux integral of this is 84. So therefore the answer is 84. Ta-da! So that's another one done. That was a lot of effort. It was a lot of effort, I know, but we made it. So, on to question 4. Another one of these Darboux integrals. Again, don't just get in the habit of assuming a certain Riemann sum will always get a certain Darboux sum, because it all depends on whether you've got a decreasing or increasing function as to which one of those things it's going to do. So, therefore, let's start by drawing a diagram. Assuming this is the t-axis on the bottom. So therefore, 6 plus 70 will look something like that. We don't know where x is, doesn't matter, but what we can say is if you do a right Riemann sum this time, conveniently, that would help us work out a Darboux sum, because again, we've got a nice continuous function that is only either increasing or decreasing for the entire interval we're dealing with it for. But crucially, because it's an increasing function this time, the right Riemann sum would be providing the upper Darboux sum this time. That's different from the last question. So that's why it's so important you do draw the diagram to make sure you're getting it the right way around with the correct labels and everything. This time, the width of each rectangle is going to be x over n. Nice. And we're going from 0 to x. And the summation is going to be really nice because this is the right Riemann sum we're doing first. That's why I like doing the right Riemann sum. It's a lot easier to do. So it's just going to be the sum. I've skipped some steps there. I'm really sorry. It's going to be the sum from r equals 1 to n of the width of each rectangle times by the height of each rectangle, which is just decided by plugging in x over n lots of r into our function. So therefore, there we go. Nice. So therefore, we can work out what that is. And then we're going to end up with a 7x squared over n squared lots of r. Cool. Applying some series formula to that stuff, we're going to end up with, oops, I've realized I made a mistake. You probably spotted it already. It's meant to be an n on the bottom there. We're going to end up with 6x over n times by n. And we're going to end up with 7x squared over n squared times by 1/2 n plus 1. So 6x plus 7x squared lots of, actually the 7 over 2 it would be technically, and then we're going to end up with n squared plus n all divided by n squared, which I'm going to rewrite as 6x plus 7 over 2 x squared lots of 1 plus 1 over n. Cool, that is the upper Darboux sum done. Onto the lower Darboux sum. Talking and drawing a diagram at the same time doesn't go well, apparently. There you go, lower Darboux sum is provided by the infimum of the function for each subinterval. There you go. Said it correct this time. Cool. So therefore, again, remember it was technically the t-axis. So therefore, the sequence of t values is given by x over n lots of r minus 1. That's just writing the arithmetic sequence of 0, then x over n, then 2 lots of x over n, so on and so forth. Therefore, the lower Darboux sum is going to equal the sum of r equals 1 to n of the width of each rectangle times by the height of each rectangle, which is just formed by doing the function with our t values plugged in. There we go, I've got enough brackets now. And then it's just a case of doing a lot of multiplying of brackets there. So we're going to end up with 6x over n. We're going to end up with 7x squared over n squared, lots of r, minus 7x squared over n squared. Cool. Now we can apply the series formula to it. I'm going to apply it to both the constant terms, so I'm going to gather the first and the last term together. Because both of those are going to need to be multiplied by n. And then the term with r in is then going to have the formula for r thrown in the mix. Multiplying out some more brackets, we have 7 over 2, lots of x squared. And then once again, same sort of thing as last time. I'm going to skip the steps because we already know it's just going to become 1 plus 1 over n, like so. Cool. So those are our Darboux sums. So interesting, it means that the integral from 0 to x of 6 plus 7t dt is going to be less than or equal to the limit as n tends towards infinity of the upper Darboux sum. Not because the limit is technically what defines an upper Darboux integral, but just because we've got polynomials, it will have the same effect as finding the infimum of the upper Darboux sum. And then equally, we want the, in fact, tell you what, let us get the proper notation in. So I'm being consistent with what we should be saying. So we're saying it's the infimum of this, and then we want the supremum of the lower Darboux sum. And as it happens, because it's a nice polynomial, yes, that is the same as just doing the lim as n tends towards infinity of the lower Darboux sum, which we just wrote out, which was 6x minus 7x squared. Was it a minus? It was a minus. 7x squared over m plus 7 over 2x squared, lots of 1 plus 1 over m. Ooh. If you're still watching at this stage of the video, huge respect to you. This ended up being a long one. Sorry. And then going all the way back to that, it's actually very similar, isn't it? 6x plus 7 over 2x squared, 1 plus 1 over m. So what this means we can now do is we can calculate the limit as n tends towards infinity. Again, n is only appearing as the denominator of a bunch of fractions in no numerators at all. So as n tends towards infinity, all the fractions with an n in disappear, meaning we basically get the same thing in both places. Same thing over here. And therefore, what do you know? By squeeze theorem, we can tell that this integral comes to 6x plus 7 over 2x squared. And I love that because you get to see in person, with your own eyes, the effect of what we're used to seeing with integration, the idea of adding 1 to the power, dividing by the new power, there for all to see. And okay, that is all the questions done. I hope you found this video useful. Sorry it was such a long one. As we said before, this video was only meant as an accompaniment to the main Can We Do That series. A link to the entire playlist for that series is on the screen right now. Do check out some of the other interesting areas of maths that we have chosen to look at before. See you in the next one.